my pleasure to introduce JJ Hermes, who is our colloquium speaker today. JJ did his PhD at UT Austin and then moved on as an ERC postdoctoral fellow to the University of Warwick in the UK, and then back to the US for a Hubble Fellowship at University of North Carolina, Chapel Hill. He is now a faculty member at Boston University. He's going to tell us cool stuff about white dwarfs. So JJ, take it away.
Awesome. Thanks for the introduction, Jen, and for hosting me for the last 2 weeks. I'm playing fill-in for the colloquium today, so thanks for the invitation on short notice. It's always fun to talk to people about things that they probably don't think about all the time. So I like colloquia. I like hearing about things that I don't work on or haven't thought about in a decade or more. And so hopefully that's what I do today is introduce some things that you haven't thought about in a while or a little outside of what you think about, just because they're fun. I like to work on white dwarf stars, and I like to think about white dwarfs in the context of supernova. And where I want to go today is a three-parter, and so I'll just tell you right away what I'm going to talk about. The first thing is that every century in our galaxy, there are a few double white dwarf mergers. So we know that rate pretty well now, and I want to talk about how we know that rate. And the second part of my talk, I want to talk about how most of those mergers don't actually produce a type 1a supernova. Most of those mergers just produce a weird white dwarf. And I'm very interested in trying to distinguish the weird white dwarfs from the normal white dwarfs. There's a lot of fun physics we can do from the normal white dwarfs, but we want to make sure we don't get contamination from the weird ones. So I want to talk about how we're doing that. And then I want to finish talking about some of the most exciting stars that I've had the pleasure of working on, which are stars that look like they're being ejected from the galaxy because they were in a tight binary and one of the stars fully disrupted and ejected the other star. So these are runaway objects that were constraining more and more. So they're kind of like white dwarfs, but they're really weird. So that's where I want to go. Feel free to interrupt me as I go along. Otherwise, I'll just keep chugging. So let's start at the highest altitude, which is, what is a white dwarf star? I'm going to talk about white dwarf stars this whole talk. And I define a white dwarf as a stellar remnant that is no longer fusing in its core. So it's no longer converting any hydrogen to helium or helium to carbon oxygen. And they're the endpoints of all stars that are low or intermediate mass. So if a star begins its life below about 8 or 10 solar masses, it will end its life as a white dwarf. And electron degeneracy pressure limits its mass to the Chandrasekhar mass, about 1.4 solar masses. And so a typical white dwarf is 60% of the mass of the sun packed into the size of the Earth. So it's mostly electron degenerate in the core, but it's also got these non-degenerate helium and hydrogen layers at the surface that we see, right? And this degeneracy pressure limit is really crucial for using white dwarfs as standardized candles. So type 1a supernova, I hope most of you are familiar, are some of the first ways we learn that our universe is accelerating in its expansion. And that's because we can use them to measure distances that are very, very large in the universe. So I'm not going to talk about type 1a supernovae today mostly. I want to talk about failed type 1a supernovae. So the same things that lead to a type 1a supernova, if that merger doesn't produce a super Chandrasekhar or even close to a Chandrasekhar mass white dwarf, you're just going to end up with another white dwarf. And we see lots of white dwarfs now that are in the act of merging. So I'm going to start talking about a system that we discovered all the way back in 2011. And it's a pair of white dwarfs that orbit each other every 12.75 minutes. So this is the system to scale. There is a 0.26 solar mass white dwarf. White dwarfs have this great mass radius relationship where the more massive the white dwarf, the more compact the object. So a 0.26 solar mass white dwarf is about the size of Neptune, and it's orbited by a 0.51 solar mass white dwarf. That's still a little bit bigger than the Earth. Maybe this is a super Earth. If you work on planets, maybe this is like a mini Neptune. I don't know. There's all this range of planet sizes. But these white dwarfs are close to that size. But they're packed into an orbit that would fit 3 times inside the distance from the Earth to the Moon. All right, so these objects are really, really close together, 12.75 minute binary. And this is what the light curve of that system looks like. So you have these really deep primary eclipses every 12.75 minutes, fairly deep, at least 6% deep secondary eclipses, You have tidal distortion of the white dwarf. That's what's giving you these two peaks. You also have a really strong Doppler beaming signal, just relativistic aberration because the system is moving at such high velocity around each other. The radial velocity amplitude is 1,300 kilometers a second in this system. So these two white dwarfs are zipping around each other. We know the system is merging because we can monitor the primary eclipse times very accurately to sub-second precision. And we've been doing that since we discovered the system all the way back in 2011. And so we've monitored the mid-eclipse time changes as the system merges due to the emission of gravitational waves. So these two white dwarfs both bend a lot of space from GR, and they're orbiting each other, so they're kind of bobbing up and down in the wake of each other's masses. That's accelerating the mass, that's giving off gravitational radiation. And we can measure its orbital period change by measuring how much its eclipses are changing, starting in 2011 all the way down to 2019. So if there were no eclipse time changes, they'd follow along this line, but the orbital period is shrinking. And so we can measure the rate of it shrinking to really, really high accuracy now. So it's about a quarter.
This is the first system for which this was measured.
This is the first optical detection. And so if we had done this before Hulse and Taylor in the 70s, we would have gotten the Nobel Prize, but
Not born yet.
yeah, exactly. It was a wink in the eye, right? So the total mass of the system is what's setting how much gravitational radiation is being emitted. And if you add the two white dwarf masses together, we don't know their masses as precisely as we'd like. That's what the 1 sigma dashed gray arrow is. And so just if we treat these as point masses, that's what's giving this gray prediction of the orbital period decay at about 0.263 milliseconds per year. And we measure 0.286. So we measure a little faster than from GR alone. So it's 1 sigma consistent with the masses, but we also expect tides to cause the orbit to shrink even faster. So tides want to keep the stars locked in orbital period. As the period shrinks, you have to spin up the white dwarf. So that's taking even more energy from the orbit. So I love this system. If you look at it in visible light and electromagnetic radiation, it's only about 5% of a solar luminosity. In gravitational waves, it's 2.85 solar luminosities. So it's orders of magnitude more luminous in gravitational waves than in electromagnetic radiation. So when we launch LISA, we will find this thing very quickly, or we will see it very quickly. All right, so we know white dwarfs merge. And in this case, this system will merge into a single weird white dwarf that is about 0.77 solar masses. That'll happen in less than 1 million years. And so there should be lots of merger byproducts that are masquerading as normal white dwarfs out in the field. I should give a shout out briefly to Kevin Burge and folks who work with the Zwicky Transient Facility. They found tens more of these really short period systems that are pairs of white dwarfs orbiting less than an hour. The shortest period system so far is a 6.91 minute double white dwarf system. They've already made 2 orbits in the time that you've been sitting in this room. So that PDOT was measured very quickly, but there are lots of short orbital period systems, but none of them have a total mass above 1.1 solar masses. So all of these double white dwarfs will merge into something that is not going to explode likely. It'll produce a pretty massive white dwarf, but it will not exceed the Chandrasekhar mass, right? So that's the first big takeaway, is that lots and lots of white dwarfs merge. I should pause if anyone has any questions about this for a second.
So how many of these have PDOT measured from the CTI ones?
So these 2 have PDOTs measured, and there's one other that has a orbital period decay measured. Okay, good. So you can simulate a population of stars all the way down to the white dwarf stage to try to get some modeling of what fraction of the field white dwarfs are merger byproducts. And some of the latest work from Temminck et al. in 2020 show that about 25% of all field white dwarfs come about from stellar mergers. Small fraction of that is double white dwarf mergers. Most of that is a red giant merging with the main sequence star, and eventually that will become a white dwarf. A lot of main sequence stars will just merge with each other over time. And so 25% of these white dwarfs should be byproducts from stellar mergers.
What's in the other category?
Triples, mostly in the other category. Yeah. So pretty fair fraction of triples as well. So I like to work on observations of white dwarfs, and before Gaia, we had a pretty limited sample of white dwarfs. We knew of about 35,000 spectroscopically confirmed white dwarfs, and most of those were by accident because the Sloan Digital Sky Survey was looking for quasars, which are faint blue objects. And so early on in the Sloan Digital Sky Survey, we got tens of thousands of white dwarfs by accident, thinking they were quasars. But now with Gaia, we can make these beautiful color magnitude diagrams where you see absolute magnitude on the y-axis. So that's distance normalized intrinsic brightness by color. And the white dwarfs really pop out in this diagram. And we now know of an order of magnitude more white dwarfs over the last few years. So we've got this great big sample of hundreds of thousands of white dwarfs. And one of the projects that a graduate student in my group, Tyler Heinz and Jen and others have been working on is actually first making sure that we are measuring white dwarf ages accurately. And a great way to do that is to look for wide coeval binaries. And so Gaia has given us more than 1,500 wide, and when I say wide, I mean more than 100 AU separated double white dwarf binaries. And so they should be coeval. They should have been born at the same time from the same material. So we find these because they're common proper motion, common parallax systems. And Gaia has given us this all sky for 1 billion objects. And so we've got this great big sample of wide pairs of white dwarfs. And so we can estimate the ages of both components and make sure they agree. And so here's a schematic showing you 17,000 degree white dwarf. That's a 0.67 solar mass white dwarf. Spent most of its time on the main sequence, that's in red, and then a little bit of its time cooling as a white dwarf. That's why it's got a higher temperature than this white dwarf below it. That's about a 12,000 degree white dwarf and is a 0.93 solar mass white dwarf. But the more massive white dwarf had a much shorter time on the main sequence because it came from a higher mass main sequence star, and it's been cooling as a white dwarf for longer. So when you add those ages together, they should roughly agree. And we see that they do. Okay. Usually the total age uncertainties we're saying are pretty good to at least 25% if you do the dumbest thing you can possibly do. But one of the real head scratchers early on is that there was a big part of this sample. So 30% of the sample had the more massive white dwarf spending less time as a white dwarf. All right, so let me run through this plot. It's a little confusing. We have two stars, two white dwarfs. M1 is the more massive component. And so that more massive component should have a longer cooling age as a white dwarf because it should have burned through its fuel faster on the main sequence. So it should be up in this top quadrant. So this is the difference between the cooling age of the more massive white dwarf and the less massive white dwarf. The more massive white dwarf should have a longer cooling age as a white dwarf. So we're trying to throw away as many model dependencies as possible. And 30% of our sample sits down here. So that's unphysical. That means 30% of the most massive white dwarfs are hotter, have spent less time as a white dwarf than the other star. It should have a longer cooling age since it was a more massive main sequence star. And so we think about 30% of our sample, these wide double white dwarfs, were actually at one point triples. And that merger at some stage actually act to reset the age of one of the components, the more massive component. All right, so we're kind of now getting into testing what fraction of white dwarfs started out as triples and are now double white dwarfs.
How big are the error bars and the ages, age difference?
Yeah, so on the age differences, these cooling age differences are very small. So these are relative. So, you know, we can measure the temperature of the white dwarf very accurately. and its cooling age is most sensitive to its temperature. There's a mass dependence. More massive white dwarfs cool a little slower, but it's mostly dependent on its temperature. So we know those pretty well. And we know the rank ordering of which one's more massive. We basically use how luminous it is in the Gaia color magnitude diagram, because more massive white dwarfs are smaller, less luminous. And so this relationship is also pretty hard to confound. So there's a pretty big fraction of these wide double white dwarfs that have been involved in some age reset, have been involved in some merger. And so now the next step is, let's look at this subsample and see, are there any clues that can hint to what a post-merged white dwarf will look like? Again, these are not behaving in the way that we would want to use these wide double white dwarfs to age date stellar populations. One of the reasons I'm here this month is to talk to Jen about using these white dwarfs to constrain the ages of main sequence stars in wide white dwarf main sequence systems. These are clusters of 2, basically. But we want to make sure we're not using white dwarfs that give us crap ages. And these white dwarfs would give us bad ages. And so we want to try to figure out ways to throw those out of our sample. Here we know because there's 2 white dwarfs, but in the field, we don't have that extra information. And so we really want to figure out what are ways we can throw out these merger byproducts. So let's talk about what most normal white dwarfs should look like. I talked a little bit about in Astro Coffee about metal polluted white dwarfs. That's a very small fraction of white dwarfs. Most white dwarfs have spectra that look just like this. You just see the Balmer series. They're called DA white dwarfs. That's the majority of magnitude limited samples of white dwarfs. About 2/3 are just hydrogen, and that's all you see. All the other metals have settled out of the atmosphere. So that's very common. White dwarfs just have hydrogen at the photosphere. Everything else is sunk out. Their surface gravities are log G8. So metals sink out of the photosphere very quickly. We can fit these lines, they're pressure broadening, to give us masses, to give us some mean mass of white dwarfs. And this is what the mass distribution of white dwarfs look like. There's a very sharp peak at about 0.6 solar masses. So the vast majority of white dwarfs have masses between about 0.55 and 0.65 solar masses. So that's also what a typical white dwarf will look like. 0.6 solar mass. And most white dwarfs rotate relatively slowly. So I won't dive too deep into astroseismology, but that's what I spend a lot of time doing with white dwarfs. And so this is a histogram of all of the white dwarf rotation rates we've been able to decipher from the rotational splittings from astroseismology. And most white dwarfs rotate between about 1 day and 2 days. So the vast majority of pulsating white dwarfs, which we think are a representative phase of all white dwarfs as they cool and they get to the right temperature, they all rotate between about 1/2 and 2 days. So that's boring. But that tells you what a normal white dwarf is. The vast majority of white dwarfs we think are very homogeneous and are pretty boring. That's also why they're great flux standards. You don't want them doing crazy things. But a typical white dwarf, 0.6 solar masses, rotating between about 1/2 a day or 2 days, and has a hydrogen dominated atmosphere. So electron degenerate carbon oxygen core, size of the Earth, but then non-degenerate helium and hydrogen layers on the outside. So that's normal. But if we get spectra of tens of thousands of white dwarfs, we find weirdos. And some of the most interesting weirdos are very, very strongly magnetic white dwarfs. And we see that magnetism from Zeeman splitting of their Balmer lines. So some of these strongly magnetic white dwarfs show really, really strong Zeeman splitting. When I say strong, I mean tens of megagauss. And so the hydrogen these hydrogen electrons can get split by the magnetic field that they're in, giving us this Zeeman splitting. And when you have a hot white dwarf with such a strong magnetic field, I think the best consensus theory is right now that those strong fields are generated from a strong dynamo from some spin up during merger, especially for these hot white dwarfs. So we see lots of strongly magnetic white dwarfs that show really strongly split Zeeman.
The magnetic field strength distribution is not smooth.
Exactly. Yeah, that's why these these features don't look, some of them do look
No, I
smooth.
meant for the population, it was basically weak and strong, but nothing. There's no, it's not a continuous shape.
Yeah, it's a bit complicated because as you cool, the function of white dwarfs that are strongly magnetic seems to increase as you go cooler, especially below about 10,000 degrees. But above that, randomly distributed, a few percent are strongly magnetic, and most of them are very massive when they show strong magnetism. All right. So
I want to let you finish about the surface magnetic field.
Oh, yeah, just that, yeah, sometimes the topology of those magnetic fields can give pretty interesting features, and I thought that's what Chris was asking about, the distribution. So, so I think instead of kind of jumping through things, there was actually a really, really great example of a clear merger remnant that was found in ZTF in 2021 and written up by Ilaria Caiazzo, showing an extreme white dwarf on all three of these fronts. So I think it's a really, really clear example of a merger remnant. The first thing is that the composition of this white dwarf looks very strange. So this is a spectrum running from about 3,400 angstroms all the way to 5,000 angstroms here. Here's near H alpha on this side. So H alpha would be this green line right here. Typically, that's where H beta would be. And this white dwarf magnetic field is so strong that instead of linear Zeeman splitting, you're getting into the regime of hundreds of megagauss fields where these Balmer lines start to spaghettify. Their energy levels start to go nonlinear. And so this is probably a 600 to 900 megagauss, almost a gigagauss magnetic field in this white dwarf. And so these Balmer lines have been shifted around so dramatically that these features are coming from non-linearly Zeeman split hydrogen. Right? So there is hydrogen at the surface, but it's been strongly split. So it's got a very, very strong magnetic field. From its position in the Gaia color magnitude diagram, we can tell that it's got a very, very small radius. It's about the size of the moon. And so that suggests that its mass is above about 1.3 solar masses. And it also seems to show a surface spot that rotates in and out of view every 416 seconds. So it's rotating on the order of a few minutes, which is much, much faster than typical white dwarfs. So this thing has a weird composition. It's much more massive than normal. It's also got an extremely fast rotation period. And so it's very, very likely been involved in a merger that's gotten a white dwarf very close to the Chandrasekhar mass, but not quite above it. I think finding more of these is really important to try to constrain, like, what is the maximum mass of a white dwarf that can survive mergers? You know, this mass is very dependent on the temperature of the white dwarf. You can see how blue this white dwarf is. Its temperature is probably above 50,000 degrees, but the uncertainty on that is of tens of thousands of degrees. And so you have a little wiggle room on this mass. But this is what a merger remnant would look like. Yeah. Jen.
How frequently are white dwarfs that massive, strongly magnetic? Do we know that?
We don't have huge numbers. It's more than normal mass white dwarfs. That more massive white dwarfs tend to be more magnetic. I don't honestly know a good number off the top of my head that I could give you. So to flash back to this sample of weird white dwarfs where the more massive white dwarf has a shorter cooling age, so it was likely involved in a merger. Tyler and I and others have been trying to get spectra of lots of these white dwarfs to see what they would look like. And so here is that system. They're resolved. They're 62 parsec from us, but they're about 415 AU away from each other. And if you get a spectra of the fainter component that's cooler, it's about a 0.65 solar mass white dwarf. So it has a total age of about 3 billion years. And if you get a spectrum of the brighter one, which is hotter and more massive, that has a much shorter cooling age, apparently, its spectra is mostly featureless. And we think that's because it's got a very, very strong magnetic field, reminiscent of this really strong field white dwarf. Right, so sometimes you can get such a strong field that the features are basically not there at low enough signal to noise. This isn't a great signal to noise spectra, but I show here in red where the Balmer lines would be. And at this temperature, you would see Balmer lines if they were there. You don't see any helium, you don't see anything else. And so this continuum kind of gives a suggestion that this is a really strongly magnetic white dwarf. So yeah, this magnetism is a great signpost for a merger byproduct. So we don't want to use white dwarfs like this to try to say something about ages, because their ages have been reset by that merger process. Good. So the last thing that I think is a really good signpost that we're starting to develop more and more to try to get good ages to try to distinguish merger byproducts of white dwarfs from the field are their kinematics. There's a great paper from Apogee and Gaia from Makareth et al. And the Apogee team back in 2019, just giving you the idea that the velocity dispersion in the Z, the radial direction in our galaxy increases over time. So this was done with high resolution infrared spectra to measure rough ages for these objects. So as stars age, as they're older, they are more likely to get kicked up, to get stirred up by the galaxy. So they should end up with larger velocity dispersions. And Sihao Ching, who was at Johns Hopkins, now he's a postdoc at Princeton, did some great work a few years ago trying to model the transverse, so the space motion velocities of massive white dwarfs. These massive white dwarfs that are hot, they should be relatively young. So this dashed line shows what they would be if they were single star, if they were single white dwarfs. That's what their velocity dispersion should look like for a population of many of these massive white dwarfs. But as you increase the fraction of those that have undergone a merger, that merger has reset their ages, made them actually older. They should have higher velocity dispersion. So that's what's kind of fit for there in the teal. And so Sihao has actually tried to distinguish which white dwarfs in the field, as a function of all white dwarfs from their broad velocity dispersions, which ones of those have been involved in mergers. And he can even split the sample up into the mass of the white dwarf. So we can split things up into mass bins of the white dwarf to say, for 0.8 solar mass white dwarfs, for 1 solar mass white dwarfs, for 1.2 solar mass white dwarfs, what fraction of those have been involved in a merger? That is, what fraction of those have kinematics that are anomalous, that have larger velocity dispersions than you'd expect from single star evolution? So this is really cool. This is really getting us to the point now where we can say, as you get to more massive white dwarfs, something like 30 or 40% of them have been involved in a merger as you go to higher masses. And so these kinematics, modeling these kinematics especially, you have to use bigger populations, right? Because stars can just have random space motions at a small level. So if you look for objects that have older kinematics than their white dwarf ages would suggest, then that gives you good evidence for mergers. And so this is a great figure showing the total mass of both white dwarfs in a binary as a function of their merger rate, and see how, by looking at these weird kinematics, is showing that this is the merger rate of white dwarfs in these systems. And he's done some population synthesis in the background. Now we're getting to the point where we're constraining the population synthesis with these actual observations to try to say what fraction of double white dwarf mergers contribute to the actual 1A rate. So if you integrate up this population synthesis that's been calibrated with these field white dwarfs, we basically can make the statement that if you want to make 1As only with double degenerates, you can. You don't need to, but the population is big enough for that to work out, right? So that's the 1A rate there. So that's just modeling these weird kinematics.
Are there, the model has all kinds of lumps and bumps. Are there intuitive things that connect to the lumps and bumps?
Yeah, so the total mass of this system is, say, 0.5 solar masses. So you're starting out with a 0.3 and a 0.2 solar mass white dwarf. those white dwarfs have already had to undergo stripping to get such a low mass white dwarf. And so they're preferentially found in shorter period binaries. So that's what's driving this bump right here. This is creating hot subdwarfs and things like that. And so, yeah, these will eventually become hot subdwarfs and then white dwarfs. But then this is genuinely, you know, 0.2 and a 0.6 solar mass white dwarf, or a 0.3 and a 0.6 creating these. And one of those doesn't have to have gone through a stripping phase. So that,
They're just more common in that mass range. So that's right.
yeah. So this is really driven by the fact that to make two low mass white dwarfs, you have two stripping events that you preferentially have them in shorter periods.
To stay down is to make a 0.2, you had to have a stripping.
Yeah, you have to have two common envelope phases basically to get these white dwarfs. Those common envelope phases, the stars are engulfed in the atmosphere and they drag in. And so that's why you preferentially find more of those. Okay. I promised to end on some hypervelocity stars. If you've been watching on Zoom, you know, it's always hard to stay focused. So I like to talk a little, you know, put things into context with a little history. And I want to go back to how we knew about white dwarfs in the 50s and 60s, how we found white dwarfs. And we know of hundreds of white dwarfs today, which was a big part of the sample back in the 50s and 60s, thanks to Henry Gickless and others at the Lowell Observatory. So Lowell was a famous place to look for solar system objects by blinking plates. This is how Clyde Tombaugh found Pluto, just by blinking sky plates. This is a blink comparator. All the grad students are very lucky not to have to use blink comparators anymore. I find it funny that most of the people that do the proper motion surveys always have these Coke bottle glasses because they must just, their eyes must have been strained from blinking plates all the time. But at Flagstaff, at the Lowell Observatory, which is a place I go a lot now at Boston University because we have some facilities out there, was a big list of white dwarf suspects. This is the GD sample of white dwarfs. And so before Gaia, before sky surveys like Sloan, we found white dwarfs just by looking for blue stars that were hot, that had high proper motions. Because white dwarfs are so intrinsically faint, for us to see them, they must be close. So they must be moving relatively quickly against background stars that are further away. And so that's literally how samples of white dwarfs were constructed back in the photometric plate era. And so here's an example. This is GD10 from 1975. This is what GD10 looked like in 1988 and what GD10 looked like in, I'm sorry, what have I done with the dates there? Those dates should change. Can't remember how long this is. I think it's at least a couple decades. But you can basically see GD10 is moving. All the other background stars are fixed. There's one friendly M dwarf photobombing the field as well. But for the most part, most stars are far enough away that you don't see them on the sky. But now that we have Gaia, we can clean up the Gickless sample. So there were about 1,700 white dwarf suspects in Gickless's catalogs. The final one published in 1980. But only less than 400 of them are actually low enough luminosity to be white dwarfs. Most of them are main sequence stars that just have really high space motion because you know, they're probably metal poor main sequence stars, halo main sequence stars. It seems like a lot of them got the color wrong. They're not particularly blue, but this is what we could do in that era. But I want to point out, I bring this sample up because there's a really fun object in the Gickless dwarf catalog, GD492. And it's one of the weirdest stars, I think, in the galaxy. So it's not staying in the galaxy for long. So in 20 or 30 million years, it'll be very far away from the galaxy. So if we look down on the galaxy, here's the galactic center in Y and X coordinates, and then here it is in the Z direction. So here's the sun in the disk of our galaxy. This object, GD492, it's also got a Luton proper motion name, LP40-365, and you can ask me why there are two names later. Has a radial velocity of about 500 kilometers a second. And it's got a massive tangential velocity as well. So it's moving, its rest frame velocity is more than 850 kilometers a second. So it is unbound to the Milky Way. It likely crossed the plane of the galaxy about 5 million years ago. And so if we try to trace back its past trajectories, now that we know its radial velocity and its tangential velocities, it came nowhere near the galactic center. So most of the unbound stars in our galaxy interacted with the supermassive black hole in the center of our galaxy, and that's what's given them very high ejection velocities. This thing did not come from anywhere near the galactic center. So it's booking it, it's moving really fast. Did not come from the galactic center, but it has one of the weirdest spectra I think I've ever seen when I first saw this object. So it was discovered by Stefan Venn in 2017. It was jointly discovered by Roberto Ratti and others before it was published, but we got scooped. So they published with the name LP40-365, but everything we were doing internally was GD492. But there's no hydrogen or helium in the spectrum of this object to very good limits. It's mostly neon and oxygen and magnesium. So this break, this is not the Balmer break. This is magnesium that's driving this deadening of the flux at blue wavelengths. So this object is mostly neon in its atmosphere. And it's got, I won't go through the whole abundance analysis that we've done for this object, but its manganese to iron ratio is super solar. And the thinking is that you can really only get that much manganese if you have near Chandrasekhar mass burning. So you need densities that are high enough that only happen in the cores of massive white dwarfs above about 1.2 solar masses. So this thing was involved this object was involved in an explosion that was very near the Chandrasekhar mass. So it's not the only one of these objects that exist. These are 3 different objects. These 2, I've been talking about LP40-365, that's here in black. This is a separate white dwarf that the spectra look almost identical. It is also unbound to the galaxy. We started looking for weird kinematic outliers in Gaia, and there are a handful of these now. So these are the most metal-rich stars that we've ever found. There's no hydrogen or helium. They all have very similar abundances. This spectra looks different just because it's hotter, but its abundances are very similar to these 2. So they all likely are involved in an explosion of a similar mass white dwarf. They all have ridiculously high space motion. And if we look at their radii based on their luminosities from Gaia, they're between about 0.16 and 0.6 solar radii, and they're below 0.3 solar masses. We also have their surface gravities from fitting their lines. So we think these are subluminous survivors of an incomplete type 1a supernova. So let me kind of unpack that. The hypothesis here is that there were 2 objects that were in a very short orbital period. Both objects were compact, and one of them underwent either a complete or a near incomplete supernova, and that unbound both stars. So the orbital velocity became ejection velocity, and that's what got them to such high velocities. And so they were likely in a less than 30-minute orbital period. So we're talking tens of minutes orbital period. So let me just take a pause because that might be a lot to unpack. These are slung-shot supernova survivors, we think. So we're not sure if they're the remnants of a donor star in the system, or if there's some bound remnant of the near Chandrasekhar mass white dwarf that actually exploded. And I think we have a little bit of evidence. The abundances are really hard to distinguish those 2 scenarios. But we actually measured the rotation period of the original member of this class, GD492, with TESS. So it fell in the FFIs, and we found that it has about an 8.9 hour photometric spot. So we think there's some surface opacity change. We're not exactly sure what's causing that opacity change, but the star gets about 1% brighter and fainter every 8.9 hours. So this is what the TESS pixels look like. It's pretty faint for TESS. So we thought maybe this was background contamination, but I was working with an undergraduate at the time, Bedelia Putterman, who looked at time-tagged ultraviolet data of the system that we collected a couple years before the TESS data. And it also showed an 8.9 hour variability. So it's definitely coming from GD492. It's very likely indicative of its rotation period. And I think that gives pretty good evidence that this is actually some fragment of the white dwarf that exploded. And the reason for that is we see an 8.9 hour rotation period now, but it was almost certainly tidally locked at the orbital period at the point of the explosion. And to get ejection velocities fast enough, the orbital period had to be less than 20 minutes. So it had a rotation period of order 20 minutes. If it was a donor, it was about 1/10 of a solar radius before this explosion. Now it's only a factor of 2 bigger in radius. You're that close to an explosion, you're going to inject some entropy, you're going to puff out the star. So it could have expanded some, but its rotation period is way too slow, I think, for it to have been a donor. If it was the white dwarf itself, it would have had a much, much smaller radius. So a near Chandrasekhar mass white dwarf has a radius that's less, that's a few thousandths of a solar radius. And so its radius would have expanded much more to get to the size we see now. And so if angular momentum is mostly conserved in the system, then that rotation rate we see now could coincide with it having been tens of minutes rotating before the detonation. So that adds some evidence that this was likely the bound remnant, the leftover chunks of some white dwarf that exploded pretty near the Chandrasekhar mass. Jen.
How should I understand the metals in the spectrum? I'm used to thinking about metals in the context of the disease that you're talking about this morning. But here, I don't think that intuition is correct.
That's right. Yeah. So these metals are probably innate from, they're the photosphere of the star. So it's really hard to know, what's going on for the whole bulk composition of the star. This thing has been involved. There's been such violence to the star on such a short timescale ago that, yeah, it's very unlikely that these metals have been accreted from any other source since the explosion.
But there's not been enough time for them to settle either.
So this thing has a surface gravity of log G5, log G5.5, and it's rotating less than 10 hours. So it still probably has some rotational support to prevent.
There's nothing to settle in.
Well,
But if it's a helium core donor, right? If it's a helium donor star, that's the thing I was.
No, so he's saying it's not.
yeah, well,
You're saying it's not, so.
It's really hard to say with any sort of convincing certainty whether it's the actual fragments of the white dwarf that were unbound or not. I think the nice thing here is we get a decent mass from the surface gravity, the luminosity, and the temperature. The luminosity and temperature give us the radius, and that radius and the surface gravity give us some mass estimate. And if you have a 1.3 solar mass white dwarf with a 0.5 solar mass donor, that total mass in the system is about 2 solar masses. And if you unbind more than a solar mass of material, you still would end up with a 0.2 or 0.28 solar mass chunk of a bound remnant. So it does seem quite plausible that this is some bound remnant of a type 1ax type supernova. So an underluminous supernova, some piece of it that's left over. And I think the rotation gives us, a slight bit of evidence that the object that we see now must have had a pretty small radius before it inflated to the size we see now. And that makes a lot more sense if it was a white dwarf rather than some helium star donor.
I have a slightly dumber question. Why is the radius measurement so uncertain? If you go back.
So here,
Well,
yeah. So this was the range of radii. Sorry, I should have mentioned that. Of the three systems that we have, their masses range from about 0.2
okay.
to 0.28, and their radii range from about 1.16 to 0.60.
Okay.
Yeah, sorry. Great. So I could talk your arms off about these surviving white dwarf systems. We also, Ken Shin, a few years ago, found some hypervelocity objects in Gaia that are almost certainly the donors. And in fact, one of those systems does have a rotation period measured. Vedant Chandra just wrote a paper a few months ago, and that rotation period is consistent with it being the donor. So there are flip sides to the system, right? There are two objects that are in orbit around each other. They're both going to get slungshot. We should see both components at some point, just
They're able
randomly.
to trace it to the remnant.
Well, there is a supernova remnant that's close to one of those objects, and you know, I can buy you a beer if we think that that's actually associated or not. But yeah, exactly, yeah. Okay, so I covered a lot of ground, so I want to come back to a summary here. So about a quarter of all white dwarfs that we see in the field will have interacted or been involved in a merger at some point in their past. And so every century, a few of these double white dwarf mergers will happen in our galaxy. And we can pick out some of these merger byproducts by looking for really strongly magnetic white dwarfs or really rapidly rotating white dwarfs. And so we've been trying to use K2, TESS, Gaia now, other ground-based surveys to try to measure really rapidly rotating white dwarfs to try to build up a population of these rapid rotators so that we can have a census of you know, objects that have gone through mergers. These kinematics are also going to be really helpful to help us distinguish what are apparently young but actually old white dwarfs. And we're getting better and better at that and modeling those kinematics. But crucially, those kinematics can also show us really, really big outliers. And we're finding more of these partly burnt supernova shards that are likely connected to at least underluminous type 1a events. So exploding white dwarfs that didn't fully disrupt, but it did unbind the binary. And so that's what gave them these big kicks. And so that's what we see today. And that's this great artist impression I showed at the beginning from Mark Garlick. So with that, I'd love to take some questions, and I'll be around for the rest of the week if you have want to talk further. So thanks.
All right, let's have a question from a student first, as is our tradition. Okay. Jason.
Maybe this isn't feasible, but I'm curious if it seems like these roughly featureless spectra are potentially indicators of these high magnetic fields, and potential merger byproducts. Are any of like the Gaia BPRP spectra going to potentially be good enough resolution or signal to noise to look for things that at least don't seem to have obvious broad lines?
No, that's a fantastic question, is whether the Gaia BPRP or spectra can help us distinguish these featureless spectra. To be honest, it's been a bit tough to even pull out whether an object's a DA or DB, whether it's hydrogen or helium dominated from those spectra. Problem is first that these lines are pretty broad, and those spectra are kind of weird polynomials rather than actual spectra, right? And the other, these white dwarfs are pretty faint, and so we don't have a ton of them. But yeah, I think that's a great way to try to find more of these featureless spectra. Now, as white dwarfs cool, as they go to cooler and cooler temperatures, at some point, all white dwarfs turn into featureless spectra below about 5,000 degrees. The photons just don't interact with anything in the atmosphere, so you just see a featureless spectra. We call those DC white dwarfs. A lot of flux standards are DC white dwarfs. But at the hot end, above 10,000 degrees, you would see stuff in the photosphere, and we don't. So that's a good distinction.
Are there Marvel white dwarfs?
I'm sorry? Oh, Marvel, wait, DC, gotcha. Yeah. Rim shot.
Did you have a question, Mark?
Yeah, I did.
Hey.
These magnetic mergers, they remind me basically like the analogs of young alpha giant steps. My question is, have you looked at seismology? Have you had the chance to get spectra powers typically? How do they compare to ordinary white dwarfs?
Yeah, so we are very certain that if you had a 12 megagauss field, you would completely suppress the convection zone. And so you wouldn't get driving. And so we've never been able to do seismology of a strongly magnetic white dwarf. The closest we've come is we've seen a spot in a pulsating white dwarf. So we see the magnetic field is strong enough to put metals at a pole to give us a spot, but we still see pulsations. But we don't see any Zeeman splitting at all in that star. So the field strength must be really, really low. So yeah, unfortunately, we don't have good constraints on seismology of these things with strong fields. Now remember, these are surface fields, and it's very likely that there's some fossil field deep in the star that hasn't diffused its way to the surface yet. And at some level, you know, we could argue about playing the same game as the suppressed dipole stuff, or you know, other things like this to try to get at the internal fields. But you know, we already have so many free parameters in our fits that, yeah.
Yes. Yeah, my question is also about these white dwarf binaries, one of which appear to be merger products. So presumably before the two white dwarfs that merged actually merged, you would have had a triple system where are these systems in a range where you think Kozai-Lidov would have been operating to merge, cause the merger to happen, and therefore could you use in the future the Gaia measurements to get any evidence of eccentricities in this wide binary to confirm that hypothesis?
The short answer to your question is I don't know. The long answer is that we actually, so one of the big things Tyler did as part of this paper was to look for triple systems with two white dwarfs and a main sequence companion, because those also have two white dwarfs. We see lots of I say lots, we see a few dozen of these widely separated triples. So I honestly don't know a good way to constrain whether or not, like, these systems have, I think what would be interesting is to see what is their separation compared to the separation of these systems, and see if there's any like statistically significant difference. I don't think we've done that, so that might be worth doing, but maybe we should chat a little bit more about what idea you have there, because yeah.
So I'm trying to understand this plot as well. And one of the things I'm trying to understand is, why is the scatter symmetric, right? So if the story holds up that the bottom ones are the ones that were triples and the merger and if I have strong magnetic fields, then why are those not stronger outliers in one direction? What is the scatter in both directions? Right, the ones at the top are normal.
So if you have a component system, yeah, I guess you would expect to scatter in this direction, right? So if you have a 0.6 solar mass difference between the white dwarfs, is the difference between a 1.5 solar mass star in the main sequence and a 7 solar mass star in the main sequence. So their cooling age difference is going to be really big. So that's what's giving you the scatter on the y-axis, is the difference in the cooling ages. And if the system is coeval, which we think they, you know, most of them should be, then that difference in cooling age is really belying something about the difference in the initial masses of those two components. I guess I'm trying to visualize the asymmetry you mean in this direction, or?
I mean like this, right? Across.
Yeah, across the zero line, because the ones above are fine, but the ones below, when underwent some merger scenario, they're triples. So.
Yeah, so one of the, you know, we have
just the age uncertainty, the uncertainties in the cooling edges that make things scatter. And
so there's also each point will flip up here depending on if this is the typical mass uncertainty that we have. And if we've not defined the prime, this error bar is a little bigger for strange reasons, but if we've not defined which one is the more massive component correctly, you know, and certainly that'll happen, then it'll.
Oh, yeah, okay.
So that's partly driving things. It's a weird, we never found a clear way to plot this without breaking our brains, because it's like,
show the distribution of the points on the left go near the Gaussian core.
exactly, yeah. So there's a histogram in the paper that probably shows this better, where yeah, you see this nice Gaussian core, and then there's this big tail of systems. Yeah.
I want to give folks on Zoom a chance to ask questions. I can see if you raise your hand.
Could I ask a quick one? Could you please show again the spectrum of GD492? Okay, here is my question. How did you conclude that neon is a dominant element?
Yeah, so there's not much neon in this portion of the spectrum, but there's definitely a lot of neon in this object. Is that a simple enough answer?
So the lines are somewhere else.
Yes.
Okay.
Yep.
If you go back to the Zeeman splitting that shows the complex morphology.
Yeah.
So presumably that smooth features outside is basically due to field morphology. But my question is, those little wiggles, do they move with time? Like basically, do you get small scale variations in strength that
Yes.
change as function of time?
We see lots of, when we see strong there are objects that show, like especially this object that has this short rotation period. Ilaria has dozens of these objects, and all of them show spectral variability at the rotation period, if that's what you're asking. Because yeah, we see different field strengths because the topology isn't homogeneous, and so as the star rotates, we see different effective field strengths. And so yeah, you see these lines move all around.
So when you reconstruct the topology on the surface, does it change with time?
Oh, no, I mean, it changes with rotation phase, but we haven't seen evidence of it changing over time. Yeah. I mean, we don't have really long baselines, but yeah. Be a fun experiment.
I'm not sure if you mentioned this, but is there any correlation between the type, so DA, DB, and how magnetized it is? So hydrogen versus helium, or does that correlate with the magnetization of the white dwarf?
Yeah, so it's really hard to. No, there's not a big correlation. It's easiest to detect Zeeman splitting in the hydrogen lines. The effect increases as you go red, and so H alpha is usually where we see it first, and so that's the observational bias for DAs, the hydrogen dominated ones. Yeah.
So I know you didn't talk about it, but for many years now, I hear about using neon white dwarfs, which would come from evolution of, let's say, 7 solar mass stars. We have discovered them.
Oh, you mean the core, like oxygen, like magnesium, like oxygen neon core?
You can make master white dwarfs by merger, but of course they would not have that composition, or you can make them in single cell evolution.
Right.
Does nature actually do that?
Well, I mean, you know, we don't know what the core of this object is. We don't know what the core of.
I know, but it's a merger problem. But is there a 1.3 solar mass white dwarf that is not a merger problem?
So, you know, there's two problems with trying to answer that question. Are there 1.3 solar mass white dwarfs that are merger product? The first is you could try to use a mass radius relationship because those are subtly different between carbon oxygen core white dwarfs and oxygen neon core white dwarfs. But our parallaxes aren't good enough to do that because these things are faint. Some of them pulsate at those massive temperatures, but the cores start to crystallize at higher temperatures. The cores actually start to become solid. And so the ones that we could try to distinguish, by the time they get to a cool enough temperature to pulsate, their cores are mostly crystallized. So we can't see what the deep core is actually made of. And so we can't actually test if it's oxygen neon core or carbon oxygen core. So far, we don't have any definitive evidence of oxygen neon core white dwarfs. You know, we have no suspicion that they're not there, but yeah, we don't have any good like direct observational tests.
All right, let's do one more question in the back before we release JJ for lunch.
So for the high velocity unbounded star that you mentioned at the end, I didn't get what you meant with incomplete type 1A supernova.
Yeah.
Possible.
Yeah. So basically, what I mean by an incomplete type 1A supernova is that there was an explosion. There was a supernova explosion that unbound most of the mass of the star, but it didn't completely unbind the star. There's still some remnant left. So that's what I mean by incomplete. Yeah. And so a lot of times you hear about bound remnants, and that's in the context of type 1AX supernova. And that's essentially what I mean. But then the binary did get unbound. So there's two types of binding. There's the white dwarf that mostly blew up and some bound piece of that left over. But then the white dwarf and the donor were in close orbit. And then when the supernova happened, they both got slung shot in opposite directions. And so that unbinding did happen, we're pretty sure.
Okay, thanks, everybody. We're
Cool.
gonna take
There you
a
go.
bit of lunch. Let's give them a show.